Okay, now let's see the second topic about the principle, how to work about the BGP protocols. The first is we have to know the concept about the BGP peer. If one router and we deploy the BGP protocol, and this router we call it BGP speaker, or maybe you can call it to become BGP router. And between two BGP routers, if we establish the neighbor relationship, we call they are BGP peers. And you also can call them to become BGP neighbors. This concept is same with OSPF and ISIS. We must to find our neighbor, and then we can do the next step. And only between the BGP peers, we can exchange the BGP routing table and get lots of routing information. So pay attention about this one. And we will divide the BGP peer to become eBGP and iBGP. Depends these two speakers located in the same AS or different AS. So this is the relationship. For example, in this topology, AS100, we have three routers, but only R1 and R3 establishes the BGP relationship, runs the BGP protocols, and R4 in the AS200 also runs the OSPF also runs the BGP protocol. And in this topology, if we want to establish the relationship between R1 and R3, because they are in the same AS, so we will call them to become iBGP peer. And R3 and R4 in different AS, so they will become eBGP peer. So this is a BGP peer. And then about the eBGP peer, we call if they are located in different AS, we will establish the eBGP peer. So when we do the configuration for AS, we must to let the router know what is your AS and what's your neighbor AS. So this is the concept about the eBGP peer. And the eBGP peer relationship is generally established using the directly connected interface. That means if Route 3 and Route 4 want to establish the eBGP peer, we usually use the physical link to connect with each other to establish the neighbor. And pay attention, if they are not directly connected with each other, for example, between them, we have the ISP, we have the, or maybe the other devices, divide them into different segments. You must to change the max hop. Otherwise, they cannot establish successful. So pay attention about this one. And another one is, if we establish the eBGP peer, then we will send out the routing information, right? And the eBGP routes, the administrative distance value is 20. So as we talk in the RCNP course, the administrative distance value smaller is better. So the eBGP will has high priority, okay? So pay attention about this one. Maybe if in your network, you have lots of paths to visit the same destination, they will choose the eBGP because the administrative distance value is smaller. So pay attention about this one. And the second one is the iBGP peer. iBGP peer means if two BGP speakers, they are in the same AS, they will establish the iBGP relationship. And usually, pay attention, when we establish the iBGP peer relationship, we want to use the loopback interface. Because the loopback interface is a logical interface, it is lower possible. Maybe the loopback interface is done, right? if your devices is working, the loopback interface is working. Okay, so like the route 1 and route 3, they can establish iBGP peer by the loopback interface. But pay attention, your peer can cross routers, but you have to make sure your TCP connection is reasonable. So this one is very important, because in the eBGP, we suggest to use the direct routes to connect with each other. If your interface is up, your direct route is working. And if you use a loopback interface to establish iBGP peer, you must to make sure your TCP connection between two loopback interface is reasonable. So that's why in the AS, within the AS, if you want to establish the iBGP peer, you still have to run the OSPF protocol. The most important function is make the loopback interface TCP connection reasonable. So this is the reason. And if we establish the iBGP peer, we don't have the limit of max hop. It is different with eBGP. And another one is the administrative distance of iBGP router is 200. So the IGP routes inside an AS are better than the BGP routes. So pay attention about this one. eBGP route and iBGP route, the administrative distance will be different. Of course, you can use some command to change the default administrative distance. It also can work. And then let's see the next step about the BGP protocol packets, because how to find our neighbor, how to establish the iBGP or maybe eBGP, and then how to exchange the routing information. Between two routers, they must to exchange BGP protocol packets. So about the BGP protocol, these packets are sent in unicast mode. Okay, so this one is very important. That's why two routers establish the BGP relationship, you must to make sure your TCP connection is ready, because this is a unicast mode. And another reason why we can establish relationship over the other routers, because we only find our neighbor by the unicast message. And the encapsulation is the BGP protocol will encapsulate the transport layer to choose the TCP. Okay, because the TCP can provide the reliable connection, and the TCP will encapsulate into the IP protocol. And about the IP protocol, number will become 6. That means if we delete the network layer, the next layer, the transport layer protocol is TCP, not UDP. Then the TCP will continue to encapsulate the upper layer protocol, BGP. And the port number is 179. According to the port number, I will make sure that the next step, we have to check the information with the BGP protocol. So this is the encapsulation. And then in the detailed BGP protocol packets, we will have the BGP protocol header and also the detailed packets information. And we can divide the BGP packets to become 5 parts. And about the first is the open parts. And the open packet is used to establish the neighbor relationship, because when we send out the open message, we have to negotiate some parameters. For example, I will track your AS number. Finally, to decide we establish the iBGP peer or maybe eBGP peer. So this is a packet. If we establish the packets successfully, then all the time we have to tell my neighbor, I'm still working, so please keep my routing information. And how to tell my neighbor? We will use a packets keep alive. So the open packets will be sent out at the beginning. to negotiate the parameters. But finally, we will use the keep alive message to maintain the BGP relationship. And if now the relationship is ready, then we will send out the message of routing information, right? This is the purpose why we want to use the BGP protocols. And we will use the update message to carry the routing information. Also, maybe we add some routing or maybe delete some routing. We will use the update message to send out. Okay. And in this process, if we have some special actions, for example, shut down your interface or maybe delete the configuration of BGP protocols, we will send out the notification packets. It is used to report there are some BGP errors. Okay, so the notification is sent when an error is detected during the BGP runnings. And another is route refresh. It is used to trigger the route update mechanism to ensure your network stability. So which scenario? When a routing policy changes, the BGP will trigger to request the neighbor to re-advertise the routing information. So about this package, only the keep alive message will be sent out all the time if we establish the relationship successful. Okay. And the next part for the BGP status. BGP is a little complex, and according to different status, you can do the troubleshooting. And at the beginning, if you first time to run the BGP protocol, the status is idle. Your status will become idle. And then we want to send out the open packets, right, to negotiate the message. But before we send out the open packets, we must to make sure your TCP connection is ready, because all the BGP packets will be encapsulated into the TCP. If your TCP connection is unreachable, that means you cannot send out the open packets successfully because you don't know where is your neighbor. And in this process, if we start, we will from the idle to connect. And if the TCP connection set up ready, we will enter into the open sent status, and then we will start to exchange the BGP packets. So in the BGP protocols, the TCP connection is very important. How to make sure your TCP connection is ready? You can use the tool ping. Ping your neighbor. If you can ping successfully, that means your TCP connection is okay. Then if in this process, the TCP connection fails, for example, if you want to establish the iBGP relationship, right? And you use the loopback interface, but finally, you don't have any routing information for your peer loopback address. So in this scenario, we will detect the TCP connection fails. So the status will become active. So if you deploy the BGP protocol and check your BGP neighbor status, keep in the active status, that means you must check your TCP connection. And of course, if we send out some TCP packets to establish the TCP connection and we don't have any reply, they will try to establish the TCP connection is ready or not. And the other reason maybe will go back into the idle status. And in the active status, if you add some routing information to make sure the TCP connection is ready, the active will continue go to the open sent packets. If the connector retry time expire, then we will go back into the connector status. And if the TCP connection is ready, we will go to the open sent status, right? And in this data, we will send out the open packets. And also we will receive some open packets from our neighbor. In these packets, we will negotiate some parameters. For example, the AS number is ready or not. For example, maybe in my part, I set my neighbor AS number is 200, but actually I received the AS number from my number is 300. That means the parameters is wrong, right? If the wrong parameters or maybe get some errors, we will go back into the idle status. If we receive the parameters and we still becomes the parameters is working, we will go to the next state to become open confirm. And in the open confirm packets, we will begin send out the keep alive message and also wait the keep alive message from my neighbor. If I can receive the keep alive message from my neighbor, that means everything is okay. So finally, we will go to the status to become established. The whole status, only the established status is correct. When you check your status are not established, that means you have to do troubleshooting. And another is, if you have some error information, we will go back into the idle. Or maybe we already negotiated the parameters successfully, but we still cannot receive the keep alive message from my neighbor. We will keep the status into the open confirm status. If we establish successful and some information happens, for example, the keep alive time expert or maybe update received or maybe keep alive received, these three actions, we will keep the status into the established. But if we receive some error information, for example, shut down your interface or maybe delete the BGP configuration, and we will go back into the idle. So in this whole process, some important things is, first, TCP connection is very important. If the TCP connection is broken, that means we cannot go to the next step for the BGP. The second one, if we establish the TCP connection ready, we will go to send out the open packets, and we also need to negotiate some parameters, includes the AS path, right? AS number, and also includes for example, the keep alive time expert. By default, if we don't receive the keep alive message, I remember it's 180 seconds, I will think my neighbor is broken. So if this timer is different, we also cannot establish the relationship. And another is only if the status of established is correct. The other status, you must to check what's the reason. So this is a mechanism. And also PS status we explain for idle, connector, active, open send, open confirm, and establish, right? And who will send out the message? And in idle, we only want to establish a TCP connection. In connect, we also still send out the keep CP packets. The same with active. And in the open send message, we will begin to send out the BGP open packets. In the open confirm, we will send out the keep alive message. Only the status becomes established, we can transfer the routing information by the update packets. So this is the important packets will be sent out. Okay, and there are some actions. If, for example, like the open packets, if we send out the open packets and all the parameters are negotiated successful, that means we can establish the neighbor relationship. Maybe it's iBGP, maybe it's eBGP. And then we can check if we establish the neighbor successfully, how we can find our neighbor status, right? We will have the BGP neighbor table to record the neighbor relationship. And pay attention, the BGP will send out one BGP or TCP keep alive message at an interval of 60 seconds, and the keep alive time is 180 seconds. That means every 60 seconds, we will send out one keep alive message to tell my neighbor, I'm still working. And if over 180 seconds, we cannot receive this message, we will decide my neighbor is broken, so I will delete everything. So pay attention about this one. Of course, if your network is very stable, you can make the timer bigger to reduce the bandwidth, to reduce the resources, send us a message. If your network is not so stable, maybe you can make the timer smaller. So it depends on your network. And then if you use a command, show IP BGP summary, you can use this command to check your neighbor information. And here as the BGP information for yourself, here is your neighbor information. Now in your table, you will have one iBGP peer, and your neighbor update address is 3.3.3, right? And the version is version 4. And where your neighbor location? Located in the AS 123. And another one is the TBL VAR value. If a route is updated or maybe withdraw means delete, the value will be increased. And the last one for the status. This data indicates the status of BGP session. If a session is established, the number of received routes is displayed here. Otherwise, the actual status, such as the active, is displayed. So pay attention about this one. You can use the command show IP BGP summary to check your neighbor information. Of course, before you check your neighbor status, you must to add the BGP configuration on all the routers. Except the BGP neighbor table, we also have the BGP routing table. In the BGP routing table, we'll record the information we received from our neighbor, right? And pay attention. If route 1 and route 3 establish the iBGP pair, and you can use the command show IP BGP to check the routing information. And we can see lots of routing information we used from the BGP protocol. And the very important one for the network segment. The star indicates the route is available, okay, the star. Of course, some scenarios the route is unavailable. For example, if your next hop is not reachable. And this feature indicates the route is optimal. Optimal routes must be available. We will select the best routes and use this feature to mark it. And another I in front of the segment indicates the route is learned through iBGP. And the black indicates the route is learned through the eBGP or maybe import locally. So this is the feature. And the most important feature is every route must make a stop. Otherwise, this route cannot be used and also cannot be advertised to my neighbor. And the next hop is a target network ID. That means who send out the routing information to my part. 3.3.3 from my neighbor, and 4.4.4 also from my neighbor, and 0.0.0, that's mean route 1 is the root advertiser. Okay, this is the first router to create the 1.1.1. So the next hop will become 0.0.0. And there are 3 attributes about the BGP, and we can use attributes to control the message. And also we will have one course to explain the detailed attributes. And the next step is how to generate the BGP routes, because as we know, we will have the BGP relationship, right? IBGP or maybe eBGP. Then we will exchange the routing information between different neighbors. And how to exchange the routing information? We have to make BGP route first. And about the BGP, pay attention. BGP doesn't automatically generate the route. So the IGP route must be imported into the BGP routing table. Then we can use the BGP protocols to send out the message, to send out the routing information. And we will have 2 import modes. One is network and another is redistribute. And the very important to generate the BGP route is the route must be in IGP routing entries and located in your IP routing table. So this one is very important. You have to track your IP routing table and find the detailed route, and then you can generate them to become BGP route successfully. Then you can transfer to your neighbor, okay? And then the network, that means we will generate only one BGP route because you have to network the special segment. And the redistribute means we can make multiple routes to become BGP route. For example, redistribute OSPF. That means in your IP routing table, all the routes from OSPF, we will make them to become the BGP routes and then transfer to my neighbor. So this is a different one. And when you redistribute the routing information, you also can add some policy to redistribute some, to control some attributes. So this is a function, how to generate your BGP route. And then in the transmission of BGP routing, there are some important principles. BGP transmit routing entries to BGP pair by using the update package. This one we already explained before. And the second one, there are some configuration. There are some principles when we transmit the routing information. The first is BGP only transmits available and optimal routes in the BGP routing table to your neighbor. So you can check the mark with star and dash, right? Only this routing information will be sent out to my BGP neighbor. And the second one, the routes obtained from my eBGP neighbor and will send to all BGP peers, includes the eBGP and iBGP. So I will show you one example. If there is one router, 3 routers, and the first and second router establishes the eBGP pair, and the rest of router maybe establish eBGP, maybe establish iBGP. In this scenario, if we get one route from my eBGP pair, I will directly send the information to my iBGP and eBGP. For example, this is route 1, route 2, and route 3, right? If route 1 send out one segment, 1.1.1.1/32, to route 2. And between route 2 and route 3, if we establish any BGP relationship, route 2 receives a 1.1.1 from route 1. I will send to my neighbor, route 3. Okay, so this is the principle. But if the routes obtained from my iBGP neighbor, and this route only will be advertised to my eBGP neighbor, but not the iBGP, in order to avoid the loop. And this needs to be determined if the BGP synchronization is enabled or not. And later we will explain the synchronization. For example, if we establish the iBGP peer relationship in route 1 and route 2, and route 2 and route 3, we establish the eBGP peer. If we receive the route information from route 1, this route information will directly send to my eBGP peer. But if there is another router for route 4, and between 2 and 4, we establish the iBGP relationship. If route 2 receives the segment from route 1, I only send to my neighbor route 3, but not about route 4, because we establish the iBGP peer. So this is a principle. And another is how to avoid the loop, right? Because if there is a loop, that means finally the message cannot be sent out successfully. And BGP is a advanced vector routing protocol. So the BGP uses a ciplet horizon to provide the loop inside the AS. The mechanism is the routes obtained from iBGP are not advertised to its iBGP peer to avoid the loop. That's why we use the principle. If we receive the routing information from iBGP, I only advertise to my eBGP neighbor, not about the iBGP neighbor. And another principle is iBGP does not change the next hop of the route when advertise the routing information, also in order to avoid the loop. So the principle is, if between these two routers establish eBGP peer, and within the AS200, we establish the iBGP peer relationship between two routers if they have the physical link. And then between AS200 and 300, we also establish the eBGP peer. Then if the AS300 send out the routing information, for example, the segment for 1.1.1/32. And then if the router receives the routing information from my eBGP peer, right, I will advertise to all my neighbor, includes this router, and also I will advertise to my neighbor. But according to the principle to avoid the loop, this segment will never send to my iBGP neighbor again. This is a principle. I receive the routing information from my iBGP neighbor. I will never to transfer it to my iBGP neighbor again to avoid the loop. So this is the principle to avoid the loop inside an AS. And between different AS, how to avoid the loop? We will use the AS path attribute to avoid the loop. That means between different AS, when we advertise the route information, we will add the AS number and finally to become the AS path. So like this topology, we have 4 routers located in 4 AS, right? And between them, we establish the eBGP relationship. Then if we have one network A, about route 1, I will advertise to my neighbor R3. and the AS path is 100. That means this segment from AS 100. And when route 3 receive it from my eBGP neighbor, I also will advertise to all my neighbor, includes my eBGP peer R4. So I will advertise to my neighbor. But now the AS path will change to become 100 and 300, right? And also saying R4 will send out the routing information to R2, and the path will become 100, 300, and 400. And also R2 will send out to my neighbor R1. And now the AS path will become 100, 300, 400, and 200. But at current, if route 1 receives this message, I will find in the AS path 100 is same with my AS path. So I will directly discard it in order to avoid the loop. So between different AS, we will use the AS path attribute to avoid the loop. And another one is, in some scenarios, the BGP root black hole will happen. For example, in this network topology, we have 3 AS, right? 100, 200, and 300. But in this topology, R1 and R2 establish the eBGP pair. R5 and R6 and also establish the eBGP pair. But we only establish the iBGP pair in the R2 and R5. That means R3 and R4 are non-BGP router. They don't know in our network, we already use a BGP protocol, right? And also I cannot recognize any BGP packets because we don't run the BGP protocol. So in this scenario, maybe there is a BGP root black hole. What means the result? For example, about the control plane, if we want to do the communication with each other, we must to get the routing information first, right? And how to get the routing information? This part belongs to the control plane. The route 1 will advertise the network A, maybe it's 1.1.1.1/32. I will advertise this segment to my eBGP neighbor R2. If R2 receive it, I will send the unicast message to my iBGP pair R5, right? Of course, the unicast message will be sent out through the physical link. But because R3 don't run the BGP protocol, so I will only forward the unicast message to R5, and R5 will get the routing information. And then R5 will send out the message to R6. This is a control plane. So if you check your IP routing table, you will find all the BGP routers can get the 1.1.1.1/32 successfully. But about the forwarding plane, all the router will forward the message according to the routing table. About the forwarding plane, we only can use a physical link to forward the message out. So the R2 will send out the message, and this message, the destination IP address is 1.1.1. R5 is the next hop, and R5 receive it. I want to send out the message to R2 because R2 is the next hop. But between 2 and 5, they don't have the physical link. So I will directly send the message to R3 or maybe R4. According to your next hop routing table, who will become the real next hop? For example, maybe it's R4. And when R4 receives this message, I will take the destination 1.1.1.1 to match my IP routing table. But we don't have any information here. So R3 and R4 don't know the route reachable to network A. So finally, the packets will be discarded. In this scenario, we call it BGP root black hole. All the BGP routers have the routing information, but finally we cannot forward out the message successfully. So how to solve this problem? We have to provide the BGP synchronization. The BGP synchronization means the routes learned from iBGP peer must be learned by an IGP. Maybe it's OSPF or static route or maybe ISIS. Then I will send to my eBGP peer. That means if we receive the routing information from my iBGP neighbor, I will do double check. According to this routing information, can I get from OSPF or not? If yes, I will send to my eBGP neighbor. If no, I will not send to my neighbor. Because finally, if I send to my eBGP neighbor, I still cannot forward the message successfully. So this is the BGP synchronization. And about the BGP synchronization is disabled by default. That means we don't check. We will directly receive to my iBGP neighbor and then send to my eBGP neighbor. Okay. So this is BGP synchronization. If BGP synchronization is enabled on the R5, even though the R5 receives the BGP information from R2, but I will not send to my neighbor, right? I receive from R1, R2 will send to R5, but double check about the iBGP routing and also the OSPF routing. I cannot learn from OSPF, so I will not send to my neighbor again. So this is a BGP synchronization. Okay. And if we don't have the routing information, we cannot forward the message successfully. Because finally, our purpose is we want to send out the message successfully. How to solve the black hole, the root black hole information? How to solve this problem? We have two solutions. One is provide the root redistribution. That means if R3 and R4 can get the routing information, finally, although R5 receives a data message from R6, R5 sent to R4, R4 still can have the routing information and forward the message to R2. We can solve this problem. So R2 and R5, you can redistribute the BGP to become IGP and then send to your iBGP neighbor, your IGP neighbor. That means I get the 1.1.1.1 from R1 by the BGP protocol. Then you redistribute the BGP into OSPF. Route 2 will send the OSPF routing information to R4 and also to R3. So 4 and 3 also will get the routing 1.1.1.1 information. So I can forward it out the message successfully. This is a solution for route redistribution. And pay attention, because if you use BGP protocol, that means you have lots of routing segments, maybe over 10,000. If you redistribute all the BGP to become OSPF, maybe your Route 3 and Route 4, the performance is not enough. So if you want to use the redistribution, please also take the policy to select some special routes to become OSPF and then to let your IGP neighbor get it. So pay attention about this one. But use the route redistribution, you can solve the problem of the route black hole. And another solution is maybe you can establish the iBGP full mesh. Full mesh means between all the routers, you have to establish the iBGP peer, like this one. So in this scenario, maybe Route 2 receive the segment information from R1. R2 will send to all my iBGP, includes R3, R4, and R5. And R5 will send out the routing information to my eBGP R6. So in this solution, R3 and R4 also will have the routing information about the 1.1.1.1. So finally, we can help to force a message to the correct destination. And in this scenario, pay attention. If you have lots of router, for example, 3, 4, 5, 10, or maybe 20, the configuration will be very complex because each router, one router must establish all the relationship with all the routers. So it also will take a lot of resources because you have to send out the open packets to do the negotiation, and also have to send out the keep alive message every 6 seconds to keep the BGP relationship. So this also have some disadvantage, but these two solutions can solve the root black hole problem. And that's all about the basic principle of the BGP. And later, we will explain some key configuration of the BGP to master the BGP principle better.